Uh, Welcome to the Investigating the L-Space Conjecture session of the conference. My name is Xinghua Gao. I'm a postdoc at Korea Institute for Advanced Studies. Before the talk, I would like to thank the organizers for hosting this conference and inviting me. In my talk, I will talk about the orderability of Dehn filling. In the first part of the talk, I will focus on definitions and especially PSL2R2 representations. And in the second part, I'm going to focus on proofs and applications, and I will show some pictures. Perhaps you have already heard about the L-space conjecture from other people's talk, but just to be complete, I will state it again here. The L-space conjecture was first introduced by Boyer, Gordon, and Watson, and says that a reducible rational homologous three-sphere Y is not an L-space if and only if its fundamental group is left orderable. Here, a closed three-manifold is called a rational homologous three-sphere if its the rational homology groups are the same as those of the three-sphere. Okay, what is an L space? For a rational homologous three-sphere Y, its first homology group with Z coefficients has finite elements, and there's an inequality which says that the dimension of the hat version of Higger-Floor homology of Y is greater than or equal to the number of elements in its first homology group with Z coefficients. Okay. Here, the hat version of Higger-Floor homology is the simplest version of Higger-Floor homology. We don't need to know the exact definition. We only need to know that it's a vector space over the field of two elements. Okay, and when this inequality becomes an equality, we will call Y an L space. So L space has the minimum possible Higger-Floor homology. Next definition is left orderability. So a non-trivial group is called left orderable if there is a strict total order which is invariant under left multiplication, which means that if A is smaller than B in the group G, then if we multiply any element C from the left, then C times A should still be smaller than C times B. And for countable group G, being left orderable is the same as the group G acts on the real line by orientation preserving homeomorphism. And a three-manifold is called orderable if its fundamental group is left orderable. I'm going to focus on the left orderability side of the conjecture in this talk. In general, how do you determine whether a fundamental group is left orderable or not? Well, we can use this theorem by Boyer, Robson, and East. It says that the fundamental group of a compact connected P2 irreducible three-manifold is left orderable if and only if there is a non-trivial homomorphism from the fundamental group to a left orderable group gamma. So as long as you can construct a non-trivial homomorphism from the fundamental group to a left orderable group gamma, then the fundamental group is left orderable. But in practice, what left orderable group gamma should we choose here? Well, one choice is to use the group PSL2R tilde. And now let me tell you what it is. We know the group PSL2R acts on S1 by Mobius transformation and we can lift this action to the real line by extending the action by integral translations. And this action on the real line defines the group PSL2R tilde. Okay. So PSL2R tilde is left orderable because it acts on the real line by orientation preserving homeomorphism. And PSL2R tilde is the universal cover of PSL2R and SL2R as Lie group. But unfortunately, PSL2R tilde is a nonlinear Lie group, which makes it difficult to study. But it's still much simpler than the group homeo R. So we can choose PSL2R tilde as the left orderable group gamma when we apply the theorem. Okay, so now we can start from a non-trivial representation from the fundamental group to SL2C, and then we can restrict to images with real traces, and then we get representations of the fundamental group into either SL2R or SU2C, and then we can pick those representation that's actually SL2R, and if we are lucky, then we can lift this representation to PSL2R tilde, and then we get a non-trivial representation of the fundamental group into PSL2R tilde. Another technique we will use to show left orderability is called Dehn surgery. For simplicity of notation, we will denote PSL2R by G and PSL2R tilde by G tilde. We will start from a knot complement M. It roughly look like this. The boundary of M is a torus. So we could draw the meridian and the longitude on the boundary. Let R equals P over Q be a rational number, where the P and Q here are coprime. And we can look at a curve on the boundary which goes around the meridian P times and around the longitude Q times. This is called a curve of slope R. To get a closed manifold from the knot complement, all we need to do is glue a solid torus back along the boundary such that the meridional curve on the solid torus is taken to the curve of slope R on the boundary. And this is called a Dehn filling of M along curve of slope R. And if we compute the homology of the Dehn filling, we can see that the Dehn filling is a rational homology sphere, which is abbreviated as QHS. Okay, but why do we need to do this Dehn surgery to get rational homology sphere? This is because for knot complements, there are usually lots of PSL2R representations, and they all lift to PSL2R tilde. So in this way, we can get many PSL2R tilde representations of the knot complement. We can pick rho tilde to be one of those PSL2R tilde representations of the knot complement. However, rho tilde may not induce a representation of the fundamental group of the Dehn filling. This is because the fundamental group of the Dehn filling is only a quotient of the fundamental group of the knot complement. And there is a kernel of this quotient map, which is generated by the curve of slope R on the boundary. And we need to make sure that this kernel is mapped to identity under the representation rho tilde, so that rho tilde can induce a representation of the Dehn filling. So we could start from knot complement M, and then construct a class of PSL2R tilde representations of the fundamental group of M. And then we will test for which slope R will the kernel vanish. And if the kernel vanishes for some slope R and for some representation rho tilde, then we know the Dehn filling of M along curve of slope R is orderable. Before I turn to the next page, notice that the inclusion of the fundamental group of the boundary of M into the fundamental group of M induces a restriction of the PSL2R tilde representation of M to a PSL tilde representation of the boundary of M. So to study when does the kernel vanish under rho tilde, we could restrict rho tilde to the boundary of M. Now we restrict rho tilde to the boundary of M. Recall that for matrices in PSL2R, there are 4 types: elliptic, hyperbolic, parabolic, and plus minus identity. A matrix is elliptic if the absolute value of its trace is smaller than 2. And an elliptic matrix acts on S1 by rotation. Okay, so there's no fixed point. An elliptic matrix has absolute value of trace greater than 2, and it acts on S1 with 2 fixed points. What's this? And a parabolic matrix has absolute value trace equals 2, and it acts on S1 with only 1 fixed point. Okay. And we can classify elements in PSL2R tilde accordingly. So an element A tilde in PSL2R tilde is said to be elliptic, hyperbolic, or parabolic if the projection to PSL2R is of the corresponding type. And it's said to be central if it projects to plus minus identity. So an elliptic element of PSL2R tilde acts on the real line by translation. Yeah, so you can lift this action from the circle to the real line. And an elliptic element of PSL2R tilde acts on the real line like this. Circle. Circle. The circles and crosses could be translated. And parabolic, so a parabolic element of PSL2R tilde acts on the real line. This And these circles could also be translated. And finally, central elements of PSO2R tilde are just integer translations. Okay. For elements in PSO2R tilde, we could define the translation number. Let G tilde be any element in PSL2R tilde, and here is the exact definition for translation number. So it's like you first pick some random point x on the real line, and then apply G tilde n times 2x, and then measure the distance between the new point and the original point x, divide the distance by n, and take the limit when n goes to infinity. So roughly speaking, the translation number measures how far away a point on the real line is moved by G tilde. And in particular, this definition does not depend on the point x you choose. Now let's look at the translation number of different types of elements in PSL2R tilde. If G tilde is elliptic, then as we said just now, G tilde acts on the real line by translation. So the translation number just measures how far away G tilde moves a point on the real line. Okay, so the translation number of an elliptic element could be any real number. But the case for hyperbolic and parabolic is very different. If G tilde is hyperbolic, then it only measures how much it moves for these special type of points on the real line. So 1, 2, etc. So for hyperbolic elements, the translation number can only be integers, and it only measures how much these special points are moved. And for if G tilde is parabolic, then it also only measures how much these special points are moved. So it's also an integer. And for the central element, they act on the real line just by integral translations, so they can only be integers. And therefore, for hyperbolic and parabolic elements, the translation number will lose some information about the action on the real line. Now we can look at the restriction of rho tilde to the boundary of M. Let's look at the image of the fundamental group of the boundary under rho tilde. This is an abelian group, and it's because it's the image of an abelian group, the direct sum Z. Okay. This abelian group can only contain one type of the three types of elements in PSL2R tilde and plus the central element. This is because these three types, elements of these three types would not commute with each other. They can only commute with elements of the same type. And central elements can commute with all. Okay. So we could say on a PSL2R tilde representation, rho tilde is elliptic, hyperbolic, parabolic, or central when restricted to the boundary if the image of the fundamental group of the boundary contains the corresponding type and plus the central elements. So for example, if the image contains only hyperbolic and central, then we will say this representation is hyperbolic when restricted to the boundary. Okay, but why do we need to classify these representations into elliptic, hyperbolic, parabolic, and central? This is because our goal is to study PSL2 arterial representations of M. And so I want to parameterize these representations. However, if the restriction of the representation to the boundary belongs to different types, then my parameterization needs to be adjusted accordingly. In the second half of my talk, I'm going to tell you how to parameterize these representations. Okay, so this is the end of the first half of my talk.